Hello, my Geodesy friends. Welcome back. So let's get into horizontal datum conversions. We've been discussing the vertical datum conversion and how to work with, going from heights in one system to heights in another. It's important to note out that what we just worked on was vertical datum conversion, which is heights only, right? We recall that in the example and in the method that we derived, there were no XY coordinates that we ended up with, right? So we really weren't concerned about what the northings and eastings or the XY coordinates were in specific, except how they define the datum. And then we provide the rotation and the translation to get to the heights of our second vertical datum. So vertical datums are heights only. Horizontal datum conversions we're only concerned about deriving our northings and eastings or XY coordinates. So we want to derive northings and eastings or X and Y coordinates, depending on what datum we're moving from and what datum we're moving to. So when we're talking about horizontal datum conversion, there are several cases we could consider. And we're going to zero in on one method dealing with the 29 to the 88 or back the other way. I'm going to scoot this up. And so when we are moving horizontal datums, there's a few cases that we have to consider. So case one. In case one, we would have two datums which share or have in common the same origin and 3D Cartesian system, such as the geocentric XYZ, the ECEF. So like the Earth-centered, Earth-fixed. So the axes orientations are the same. But they have different ellipsoids. So we don't need to, in this case, we wouldn't need to think about changing to different metrics in terms of the 3D coordinate axes, the XYZ axes. So something like that might look like we have our z-axis and our x-axis and our y-axis. So this would be z, x, y, or x, y, vice versa. I'm not sure how I said it. But we have our 3D coordinate system, and of course these are perpendicular to each other, right? And in the original datum, we might have one ellipsoid centered at the center of mass of the Earth. And for the datum that we are converting to, we may have a different ellipsoid altogether that might share some common area. Like here, there would be a little difference. But in this case, we would go from, psi, lambda, latitude, longitude, and height. And then we would have to convert those to x, y, z. And this would be the old system. And then go to x, y, z that they share. So that would be the old and the new. But then we can go right to the phi, lambda, and h in the new system. So there's less conversion there. So that's case one. Case two, datums have different origins. And axis orientations. So this would be a true 3D coordinate shift. In this case, so what that looks like is we would have I'm just going to do it in 2D just to get the idea across. So here's one system, and then our other system might be something that's a bit skewed. But remember, our points are in the same place. They would just have different coordinates based on which reference frame we're using, right? So in this case, we would start with latitudes and longitudes in the old system, as we did before, and heights. And we would need to convert that to XYZ coordinates in the old system. Then convert that to XYZ coordinates in the new system, which would be 3 rotations, 3 rotations and a translation. And that translation would have 3 coordinates. It'd be a 3-component vector. And then finally convert to latitudes and longitudes in the new system. And from there we can get northings and eastings if we like. So there's an added step. We have to convert from one Earth-centered, Earth-fixed system to another Earth-centered, Earth-fixed system, having a new origin as well. And this conversion would actually be a 7-parameter. Right here, we would impose a 7-parameter Helmert transformation. So that's case 2. Now, case 1 and case 2 are both cases in which we have a mathematical way or a mathematical method to go from one datum to the next datum. But with datums, that isn't always the case. Usually we have case 3. So case 3 that's where there is no mathematical transformation. From one datum to another. And this is the case with 29 to 88 or vice versa, right? So this would be the case with NGVD 29, which is, as we've discussed, an empirical database surface datum, right? So an AVD 88. So this transformation has no perfect mathematical bridge between them. And just a note here, recall that with NGVD, it's a surface-based, and I like to emphasize it's empirically based. So what that means is that scale, point scale, and orientation vary throughout the system from point to point. Throughout the system. Okay, so what do we do in that case? Let's see. Oh, sorry, I'm still talking about vertical datums, aren't I? So we're in horizontal world. Sorry to make you scribble out and rewrite your notes to get out of vertical mode. So this would be like the case of NAD 27 to NAD horizontal datums, NAD 27 to NAD 83. So recall that NAD 27 is surface-based. So again, scale and orientation vary from point to point throughout the system. And we have a few methods for dealing with that case. So let's look at some of those methods. So methods of transforming let's see, when we don't have, when we, at least one of those surfaces is not a mathematical surface. The first one would be a minimum surface curvature fit. So we have to go to the ellipsoid and consider the ellipsoid parameters. Or we get to consider ellipsoid parameters while we're trying to fit all that data into a workable mathematical surface. And this is what's used in NAGCON. The NAGCON NGS conversion tool for coordinates. So NGS NAGCON software. There's another conversion software. It's called CoreCon. So I'll say CoreCon. And we could probably guess what that is. That's the Army's. So that's the Army's conversion tool. In general, it produces, so in general, this produces okay results. So plus or minus 0.05 meters or 5 centimeters accuracy. Which would support mapping applications. So it's decent for GIS purposes. Which mapping? Come on, Rob. I get to talking and I start writing what I'm talking and can't chew gum and walk at the same time, I guess. Which supports mapping applications. Not sufficient for engineering or surveying. So, yeah, minimum surface curvature fit. That's one method. And we're not going to go into the theory of that. It's just not within the scope of this course. Second method, method 2. This would be a 7-parameter Helmert transformation. And this tends to fit smaller areas fairly well. And with a least squares adjustment, so it does incorporate a least squares adjustment. So we have residuals as a result. Anytime we do a least squares adjustment, the value of it, one is the adjustment itself, but the second value, which is hugely important, is that we have residuals to analyze. Or verify the quality of the transformation, the specific transformation. But again, I don't think we'll have time to go into the 7-parameter Helmert transformation. We do that in, I believe, remote sensing. And if we have time, eventually I'll try to hit the 7-parameter Helmert transformation. However, it's really not, again, not within the scope of this course, nor is it as practical as method 3. So method 3. This would be the 4-parameter Helmert transformation. And the 4-parameter Helmert transformation is going to look very familiar because we actually did it before with the vertical transformation. We just use different condition equations. We're going to develop some new condition equations which will be very similar, but they're going to allow us to extract the horizontal coordinates, the northing and easting, or the x and y. So the 4-parameter Helmert transformation, which I believe is in chapter 7 of the book that we're using. In this process, we have one rotation, two translations, and one scale. So this would be the 4 parameters. Can also note that this is similar to what we've done before. Keep in mind that it's similar to what we've done before, so you can kind of piggyback on that familiarity. The symbols will be a little different. Some of the equations will be a little different, but it's a similar process. Okay, so let's get into it. Now I'll expand on this more in just a few minutes, but NAD 27 used XY coordinates, while NAD83 uses northings and eastings, and they're reversed. So I'm going to expand on that in just a little bit. But basically, what we have is the X prime and the Y prime in the old system are equal to some scale times the cosine of theta. And I'm going to write this. I'm going to go ahead and pull that scalar in, and you'll see why when we get toward the end. So remember, if we multiply a matrix by a scalar, it applies to all of the elements, all of the members of that matrix. And then we have minus sine theta minus s sine theta. And I know this looks familiar because we've used it before. So again, we're just motivating the idea. So xy coordinates of the old system. We're motivating the idea of a transformation. And then the translation. So we have one scale, that's the S, so one scale. Our matrix performs one rotation. Notice that theta, we just have one rotation angle. So we have one rotation. And then we have a translation in the x direction and the y direction. So two translations. Okay. And if I use the vector notation, this would be the x prime vector equals, this would be our b delta. So this is our delta, our b, our x prime, plus, we'll call it a t here. We're going to change that in a minute, but plus our translation vector. Super familiar. It's what we've done 100,000 times, right? Maybe not that many. And just to throw another monkey wrench in here, most textbooks and most methodologies, when you see this process, they don't use these matrices as they're shown here. But I wanted to transition from what the notation we've been using into what is more common. Notation is that bugger that is always changing, right? Seems like if we change a little something, we have to change the notation. It's like Italian pasta. If you make a different shape, it's a different name. So most textbooks use and I'm just going to write textbooks, but it's textbooks or systems, methodologies, if you see them on paper. They're going to use x, y prime, just like that, just like we have, equals a, b, minus a, or minus b, sorry, and a times xy plus c and d. So that's what we're going to work with. And in this, let's push this up and I'll label all these, where a equals s cos theta, so the scalar is in there, and b equals s sine theta. It does make for less writing, doesn't it? Now, I promised you that I would get into some of those differences between NAD 27 and NAD 28. NAD 27 and NAD 83. So some notes on NAD 27 versus NAD 83. And these are important to keep in mind as you're going through the calculations. One of the points is that NAD 27 uses coordinates in the form of x, y, with that notation, while NAD 83 uses northings and eastings. And you've probably noticed by now the coordinate components are reversed or opposite. So here, typically X, we think of like the easting, and Y, we think of like the northing. So they're reversed. And we'll develop the solution process with that in mind, okay? So it's not something that you have to visualize really, because we're going to build it right into the solution process. So just something to keep in mind. And so here's the development of the solution. So solution development. Now, one thing that we found that we needed to use when we were performing a least squares adjustment, which we're about to do, is that we need some condition equations, right? In the case of the state or in the case of horizontal datum conversion, we would have EI plus a residual equals A times X sub I. The I's are just subscripts, they're placeholders for 1, 2, 3, 4, etc. Plus B Y sub I plus C from our translation matrix, the C and the D. And these are the A's and the B's and the C's from what we just wrote down in the matrices. And N sub I plus its residual. I should put, this is EI and NI equals A times YI plus, and this is where we're building in that accounting for the reversed coordinate components, right? And sorry, that's not a plus, it's a minus. I've done that before, which I heard about, thankfully. BXI plus D. And I'll say that's for I being some integer. I equals 1, some positive integer. Subscripts. Depending on how many points we have. So some observations would be that X sub I and Y sub I are, in our case that we're building up to, coordinates. I'm going to shorten that to chords. So if you see chords, that means coordinates. In NAD 27, which as we learned uses X and Y. And then E sub I and N sub I are coordinates in nat 83. A equals S cos theta. B equals S sine theta. Theta is the rotation angle. Let's see. C and D are components of the translation vector. Which previously we used Tx and Ty prime. And then V sub EI and V sub NI are residuals. Okay, so how do we build this? Let's suppose we have 4 points. And they can, for us, we'll have 4 known points, so we can develop a transformation or a conversion. But some of those could be unknown. It doesn't really matter. Then that would look like E sub 1 plus V sub 1 equals AX sub 1 plus by sub 1 plus c. And then the northing would be n1 plus v1 equals a y I, or a y sub 1 plus b, or that's going to screw me up sometime. So far I'm catching it. Wish you could yell at me, but you can't until later. Bx sub 1 plus d, and then we'd have E sub 2 plus V sub 2 equals A x sub 2 plus B y sub 2 plus C, and E, or N. I'm not going to write all these out. And then N sub 2 plus V sub 2 equals A y sub 2 minus b x sub 2 plus d. And we would keep going. We do the E and N3, and then finally E sub 4 plus V sub 4 equals AX1 plus 4 BY4 plus C, and N sub 4 would be AY sub 4 minus BX sub 4 plus D. Well, doesn't that just smell like a matrix setup, right? I will note that, or give you that these are our condition equations, and the condition equations are what we want to build into matrix format. How do we do that? That would be a great exercise, not a difficult one. It'd be pretty easy to figure out how to put this in matrix notation, right? Let's see. I want to finish what I'm writing here. So how do we put this in a matrix? What does the matrix notation look like? And I would invite you, even encourage you to pause the video and come up with, try to come up with what the matrix equation would look like. But anyway, I'm not going to wait for it. You can pause and try it if you like. But we would have, if we had, so remember we have 4 points in this example we're building up to, and we would have our Vx1, Vx2, or sorry, y2, y1, our Vx2, our Vy2, I hope I can fit all these in here, Vx3, Vy3, Vx4, and Vy4. And that is one matrix plus x1, y1, and then just 1 and 0, and then reverse them, y1, x1, but it's a minus x1, and then 0 and 1, and then x2, y2, 1, 0, and then y2 minus x2, 0, 1, and then y3, x3. It's hard to keep these straight. x3, y3, 1, 0, and then y3 minus x3. It's not an the minus or the negative is not an operation, it's a sign. 0, 1. And finally, we have our 0.4. So x4, y4, 1, 0. And y4 minus x4, 0, and 1. And we could keep going if we had more points, right? And then we would multiply that by our delta. So A, B, C, D. And that would equal our goal, which would be E1, N1, E2, N2, E3, N3, E4, N4. And that's it. That's our matrix setup. So let's play with these a little bit. Let's take a look. First of all, do our dimensions work out? So this one is the dimensions of our first is 8 by 1, 8 rows, 1 column, plus, and this is 8 rows, 4 columns. So we can definitely add those, right? And then multiplied by 4, 1 here, dimension 4, 1. Can we do that? 4 on the inside. Yep, they match. And this is an 8 by 1. And is that what we end up with? Well, let's see. We have an 8 by 1 here. We add it to a product of matrices that's going to give us an 8 by 1. Remember, the outsides are our resultant matrix product dimension. And then so 8, 1 plus an 8-1 gives us an 8-1. Yep, it works. So the dimensions work out with this. It's always good to check. And we can name these vectors. I don't want to pull it up all the way, but these vectors we name, they're called, so this is our V vector. This is our B vector. This is our delta vector. And this is be our F vector. So that we end up with V plus B delta. Look familiar? I think so. Equals our F vector, which is the same as our vector of residuals being equal to F minus B delta. So that's how we get our, this is what we really want, because this is how we get our vectors, or our residuals. So let's do it. Let's solve that process. So we go through the same least squares adjustment process. So what is that least squares adjustment process? I should point out here that everything is equally weighted, so we're not going to worry about weights. We're keeping it simple. In least squares, in the class, least squares adjustment, we'll actually start considering the situation in which we're unequally weighted and we apply weights. But for now, equally weighted. So since it's equally weighted, we come up with our N matrix, which is the B transpose times B. And then we come up with our T vector, which is the B transpose F. And then our delta matrix is equal to the inverse of N, just like before. This is nothing new, times our T that we just did in step 2. And then finally, our vector matrix is equal to F minus B delta, which is what we came up with above. And that's it. That's the end of the process. Well, I shouldn't say it's the end of the process, but it's the end of the coming up with the mathematical transformation model. So once we have that done, we can get our E and our N of our point. So E of the unknown equals A times X plus B times Y plus C. And the unknown northing would be equal to AY minus BX plus D. And that's how we would get our final components. That's the goal. That's the holy grail. We want that new northing and easting in the datum. And I'm going to do an example, but before I do, let me just demonstrate conceptually what's going on with a horizontal datum transformation. So let's say we have our points in one datum. So here's one datum. And this is, the perspective on this is looking down on our datum. So we're not looking down on the XY axis in terms of Earth-centered, Earth fixed. So the Earth is not fixed. This is looking down on that plane that's tangent to the Earth at our centroid, like in the LBH or the easting northing up case. So we're looking down through the up axis at our centroid. So this would be our centroid, and this would be our, let's make this our y-axis, and this is our x-axis. So our new axis, remember we do 1 rotation, 2 translations. So we would rotate through some angle theta. It's not dark enough. There we go. So here's our new datum after just the rotation. And this would be our angle theta, our rotation angle. So that's the 1 rotation. But then we would translate along the x-axis. Say our new point is here, and then along our y-axis that's now rotated, so our new axis becomes this right here. So we rotated, oh, sorry, that's not right, because we translated twice. Remember, so that would put our centroid, since we rotated along the green lines, first the x-axis, then the y-axis, that would put our centroid there. And now our new final axes are here and here. Well, it's supposed to be with that green line. Just not drawing very well. There we go. Better. Anyway, so you get the idea. 1 rotation, 2 translations, and then we would scale. So usually, again, we would scale based on whatever metric we're using. US feet, we're going from US feet to meters, we would have to scale. But here's the magic thing, and I think this is really cool. When we go through this matrix format of the least squares adjustment, the scale is incorporated automatically. We don't have to think about coming up with a scale factor. That is going to come from the coordinates. So now let's do an example. I have a spreadsheet. I always have a spreadsheet, right? So let's see, this one, there we go. Now what I've done is I've went ahead and filled in, our example is these are the coordinates, and much like the vertical situation, the vertical conversion, we have 4 sets of known coordinates, or 4 sets of coordinates that are known in both datums. We have a set of coordinates in the old datum that we've derived through traverse and level loop. And what we want to do is go through our matrix process to come up with a mathematical method to get to the unknown coordinates. And I have my nice, all my formulae here. That I can refer to as I'm building this. It's super helpful. I don't have to keep looking away. I've just got it all right here. And then I went ahead and filled in my B matrix. So my first one would be, that's X1, and that's Y1, that's X1, and that's minus Y1, and then my 1s and 0s. All I did was just reference the cells above. So I went ahead and did that ahead of time, so it takes a minute to do, so didn't want you to have to sit here while I just hit a bunch of equals. So here's my B matrix with just my X1s, my Y1s, the negatives where appropriate, and then the ones and zeros. And we just go through our solution process. So first I come up with my N matrix, which is the B transpose B. So it's a multiplication. Highlight all the cells in the matrix and go equals MMULT. And then I have to transpose my B matrix, right? So I'm going to go transpose, highlight my B matrix, and then close my parentheses, comma. I'm going to multiply the transpose by the matrix itself. So I just highlight the same matrix and close my parentheses, and boom, there we go. There's my N matrix. Excel makes things so easy and practical to do. So let's see, I look at my formula here for T, and I need B transpose F. So I highlight the whole thing, and it's going to be another multiplication. So MMULT equals MMULT. And I'm going to transpose my B matrix, close the parentheses, comma, multiply it to F. Oh, I didn't create my F matrix yet, did I? So what is my F matrix? Well, remember, the F matrix is my known coordinates in NAT83, my known resultant coordinates. And I have those, right? So that equals my x1, or my n1. No, my e1, sorry. So e, and then my second is equal to my n. And my third cell equals E2. And my fourth cell equals N2. And I just keep going. Shouldn't take but a second. Just building my F matrix so I can use it. There we go. Okay, so now we can multiply, get our T matrix. So again, it's equal to a multiplication of matrices. And it's going to be the transpose of B, comma, and then my F matrix. And why did we get a fourth cell? What did I do wrong? Duh, because it is a third. It is a fourth cell. And that's the value of looking at my dimensions first. So B is a 4 by 4, so transpose would also be a 4 by 4. So we're multiplying a 4 by 8. The transpose is a 4 by 8. So let me start over. B is an 8 by 4, 8 rows, 4 columns. So the transpose would be 4 columns, or 4 rows, 8 columns. So it's a 4 by 8 times an 8 by 1. We should end up with a 4 by 1. Yep. All right. So there's my T matrix, and everything looks good. All right. So let's get our delta matrix. Delta, what is delta? That's the inverse of our N matrix times our T matrix. So equals MMU LT times the inverse. So remember, the function for the inverse of a matrix is minverse, M-I-N-V. I'm fat fingering like crazy today. Minverse of our N matrix. And we're going to multiply that to our T matrix and see what we get. Looks good. So these are our 2 rotations, or our 1 rotation through theta, and this is our delta matrix. or our translations, our two translations. And then since we have our v vector, or we have our b vector, we have our delta vector, and we have our f vector, we can do the v equals f minus b delta. So I highlight all the cells, and that equals my F matrix minus the product, so MMULT, of my B matrix and my delta matrix. And we can take a look and see how good our transformation is. Not bad. If we look at our residuals, let's see, we have a little over a centimeter in a few of the cells, or just in a couple, but for the most part, they're in the millimeters. So there's 3 of them that are a centimeter or a little more. The rest of them are in the millimeters. So not too bad. Pretty good transformation. And then here's a check, everybody. I'll highlight that in, I don't know, some sort of pink color. So see where it says sum equals 0? Well, if you've done everything correctly, if you remember way back to learning the statistics, when you calculate residuals, the sum of those residuals should be equal to 0. If they're not equal to 0, something's wrong, because residuals cancel each other out. So it's always good to perform that check. So now we have everything we need to get our easting and our northing. So the easting is equal to ax plus by plus c, where x and y are the coordinates of our unknown point in the old system. X and y are the old system. So this is equal to, we could do this in matrix format. If I had more points, I would, but I'm just going to type out the formulae. So that equals to A is right here, times x up there, plus B times my y value, which is up there, plus C. And there we have the coordinates of our first point. Now we do our n. I'm going to have to bring that back down. So our northing is equal to a times y, a times the y value, minus b times the x value, plus d. And we have, there's our northing in our new system. So we've gone through and we have calculated our coordinates of an unknown point. We've converted them to NAD83. And that's it for the conversion process. Now, since A is equal to S cos theta, B is equal to S sine theta, we can calculate our theta value and our S value, couldn't we? Super easy to do. I'm going to leave that for you to do on your own. It involves, I'll just tell you, if you take A over B, then that's going to be the tangent of theta because the S cancels out. S's cancel out. I'll just walk through that real quick. So that's not going to stay visible. If we say that, where's my pen? So A equals S times cos theta, and B equals S times y theta. Remember, A and B we have known values for, or we have calculated values, right? So then if I were to go A over B equals, actually I'm going to do B over A, otherwise I have to do a cotangent. And this is sine. What did I do here? I must have been talking and wrote the wrong thing. S times sine theta. There we go. So I'm going to say B over A gives us S sine theta over S cos theta. The s's cancel out, and we're ended up with B over A, which again are just numbers. We have those numbers, is equal to tan theta. And then take the arctan of both sides, so tan inverse of B over A is equal to theta. Now, whenever we do an arctangent, we always have to adjust for quadrant, but in this case, we don't have to worry about it because the rotation angle is never going to be more than 90 degrees. So it's just that theta. So once we have our theta, it's easy to plug it back in to either of these and then solve for S. So we can get our scale. Pretty cool, huh? So one thing that, like I said, I think it's kind of magical. You'll notice something we didn't have to do. We didn't have to worry about the fact that we're going from feet, US feet, to meters. It was all incorporated into that least squares adjustment process, which I think is really cool. The final coordinates we ended up with were in the correct metric, that is meters. Anyway, so there you have it. Horizontal datum conversion. Now we've gone through a vertical datum conversion, horizontal datum conversion, and we have the example. I have posted that example on Facebook, or I did it again. Like I said, I don't even have a Facebook. I posted it on Canvas, and it looks a little different because I built a new spreadsheet for this lecture with some different colors that highlight things a little better, but I did post a PDF on Canvas with these numbers so that you can mimic the process and build your own spreadsheet. You can use whatever colors you like. All right, so horizontal datum conversion. Next time we're going to talk about something that I kind of left dangling early on. It's another conversion, and I went one way but not the other way. I'll leave you to guess what that is. But anyway, that's what we'll be doing next time. And I hope this finds you well, and I will see you next time.